In this video, I'll teach you essentially everything that you need to know about C++ in order to use Helios. Now, it is no secret that many people who want to use Helios are very turned off by the fact that it is written in C++. This strikes fear in the hearts of many users and is a deal breaker for those who may be interested. And so in this video, I'll take you through essentially all of the elements of C++ that you need to know. Since pretty much the first day that I started writing Helios software, I knew that this was going to be an issue for many people, and so I specifically wrote it in a way that the end user needs to know very little about C++ and a lot of the more technical aspects in order to use it. So I tried to use only the most basic features of C++ that are not too different from other programming languages that users may be already familiar with. So I tried to write it in a way that the learning curve is as shallow as possible. And I've talked to and worked with dozens of people who have started using Helios with no C++ background whatsoever. In some cases, little to no programming background. And this essentially has been a non-issue. Pretty much everyone is able to pick it up no problem and start working with it. The C++ aspect is really not the barrier that most people think. So I would invite you to just give it a try, and I'll take you through what you need to know in order to feel comfortable using C++ within Helios. So first question that many people ask is, why was Helios written in C++? The main reason is for performance. There are a few aspects of C++ that make it really desirable in terms of the performance. The first being the libraries that are available. Particularly at the time when Helios was first being developed, the best high-performance graphics libraries were all available in C++. So CUDA, NVIDIA's optics platform, and OpenGL all had libraries in C++. The other thing is that a compiled language in general is often going to be preferred for speed. In many cases, it is orders of magnitude faster than an interpreted language. This may be less true today. Python has made a lot of progress in making it faster as far as still being a user-friendly interpreted language. And there are now just-in-time compiled languages like Julia, for example, that are getting more popular, that are able to kind of take advantage of the best of both worlds. But nonetheless, this is the language in which it was written, and I think the performance aspects still hold true today. So there are really 6 aspects of C++ that you need to know in order to work with Helios, and we'll go through each of them in this video. The first is just the overall program structure of a C++ program. As part of that, we'll touch briefly on namespaces. The second are variable types. Third are functions or methods if they're part of a class. Fourth are vectors. Fifth are for loops. Sixth are classes and structures. All of these, or most of these, pretty much anyone with prior programming experience should be familiar with. It's really just a matter of the differences in syntax and feeling comfortable with using the slightly different implementation that's needed in C++. So first we'll start with the overall program structure. Here is a simple classical hello world program written in C++. And we'll kind of break down the different aspects of this in order to illustrate the overall program structure. So all programs in C++ need a main function. The main function is called main, and it always returns an integer. Functions in C++ are encapsulated by these curly braces, and anything inside of that is essentially the body of your program. So this is the thing that it does. And you want to return an integer value, usually corresponding to whether the program ran successfully. We also may have header files at the top. So in C++, any functions or variables or data structures have to be declared before they're used. So a header file is essentially just a bunch of forward declarations of the different functions and data structures that are used within the program, within that particular file. So we just package all of those into a header file, and then we can just include it at the top. So you can think of an include statement basically as a copy paste. The compiler just goes in and copy pastes everything that's inside of that file right there into your actual program file. When you're writing a C++ program in Helios, it's almost never necessary to actually go through and include your own header files outside of Helios. This is because the main file that's included in any Helios program, context.h, is going to include the bulk of the most commonly used header files in a C++ program. So you can find this in the documentation. This is a list of all of the header files that are already included in context.h. So in order to use this cout, to use C++ style output to the command line, we needed this header file iostream, but it's already included by default within context.h, so we don't need to worry about including it. Very rarely will I ever need to include a header file other than just context.h or the header file associated with the plugin that I'm using. And I'll cover plugins and using the context in other videos. Another thing to mention are namespaces. A namespace is essentially just an encapsulation of different variables or functions within our program so that we don't get naming conflicts. So if we include a library such as Helios, it's going to define a bunch of different variables and functions and classes, each with the names that I've chosen. And this is all encapsulated within a namespace so that it kind of keeps it separate, so that everything in that particular library is encapsulated in that particular namespace. There's a namespace called Helios for everything that's within the Helios libraries. If you're a Python user, this will be familiar to you. So if you use NumPy arrays, for example, and you include in your header import NumPy as NP, for example, then it will essentially create a namespace called NP. And anytime you want to use a function within that namespace, you have to type NP dot and then whatever it is beforehand. Or you can just say, I want to import that directly into the namespace that I'm currently in, and then I don't have to type that NP every time. So it's very similar within C++. So if I was to add this line called using namespace std in order to be in the standard C++ library namespace, then I don't need to type this std : in front of every single call or variable that's within that particular library's namespace. All right, next we'll talk about variable types, and this is something that's different than many interpreted languages. In C++, you have to explicitly declare the type for each variable. This is pretty common in compiled languages, less common in interpreted languages. So anytime you declare a variable, you need to tell it the type. And so this basically tells it how much memory it needs to allocate for this particular variable. And so there are different types that are available within C++. You have characters, integers, unsigned integers, which there's kind of a macro definition just shortened as uint within Helios. You have a float and then a double precision value. For the most part, Helios works with floats and ints and unsigned integers. These are all common in most Helios programs. We could also declare and initialize our variable in two separate steps. In that previous example, we were doing both of those in the same line, but we could declare our variable, in which case it would be uninitialized for just a brief second, and then we could assign it a value on the next line or somewhere else within our program. This can be dangerous in some cases because if you forget to ever initialize it or set its value and you use it, then it can create undefined behavior. In some cases, it just happens to point to a place in memory that has all the bits set to 0, so it will be initialized to 0, other times not, and you can get random behavior as a result. When you declare a variable, it's only declared in the particular scope that you're in, and a scope in C++ is usually denoted by curly braces. So if we're in our main function, we're within the scope of that function. If we're in a loop, then we're within the scope of that loop. Here I've just added some curly braces just to indicate a different scope, even though there's really no point in having this. But if we had this scope defined by these curly braces, and then we declared a variable called A, and then we tried to reference that variable outside of that scope, then this would give us a compile time error because A was not defined in that scope. Once you leave a scope, then the variable is no longer defined. In C++, we also have the auto keyword, so you can let the compiler decide what the data type is. This can be convenient because then you don't have to worry about it, but usually it's recommended to just explicitly say what the type is going to be so that you can kind of understand what's going on and explicitly tell it what you want to use. Sometimes when you're dealing with things like iterators or maps or things like that, where it just takes a really long time to type out the entire type, the auto keyword can be very beneficial in this case, in which case it's usually preferred. In Helios, we often use strings from the standard library. So this is just called a string, and if you're not in the standard library's namespace, you have to type this std::: in front of it. Note that in order to use it here, we didn't have to actually include a header. If you were not including the context.h file, then you would need to include a header in order to be able to use this out of the standard library. The string header is already included within context.h, so we don't need to worry about including it. Okay, next on to functions or methods if they operate on a class. So there are some aspects of functions that may be different from other languages that you've worked with. One I kind of already mentioned, which is that functions must be declared before, or in other words, above where they are called. So there needs to be some declaration of that function. The compiler needs to know about it beforehand before you're actually using it. And then it just needs to be defined somewhere in code that's linked at compile time. One really important thing about functions in C++ is that the data types for arguments must match the definition. So when we define a function, we need to specify the data types of all of its arguments. And these need to be consistent. They need to be in the right order and have the correct types. I would say one of the most common sources of error for new users of Helios and C++ in general is that they don't supply the correct argument types or in the right order for functions. And then they get a compile time error saying that there's no function that was defined that has this combination of argument types and in this order. So the Helios documentation is the best resource for that. If you want to use some function, you can just check in the documentation. If you're using CLion, you can just kind of hover over it. It'll pull the documentation right up, and you can check what the argument types are and in what order you need for different functions. You can also have overloaded function definitions where you have the same name for a function, but it can be defined with different argument types and with different numbers of arguments. And so you just need one of them to be valid. You need to use one that has been defined. So you can have a virtually infinite number of overloaded definitions of functions with the same name, but we just need to find one that has the correct arguments that we want to use. Finally, function outputs can either be returned from the function itself or as output arguments, or both. So the function can return a value directly from it, which is maybe how you are used to it in other languages like MATLAB or Python. But you can also have arguments of the function be outputs. They can modify the value of that variable and then pass it back out of the function. So there's different ways of doing that to be aware of. This can make it a little bit confusing to know which arguments are inputs and which are outputs. In the Helios documentation, this is designated explicitly. So as it's saying what each argument names correspond to, it'll say whether it's an input, an output, or if it's both an input and an output. In this example shown here, we have instead written a function to say hello. So this is sort of like a hello world, but defined within a function. And so our function here is called say_hello. It takes one argument. That argument has type of string, and the name of the argument is just name. So we pass it a string, and then it prints to the command line hello, and then whatever name or whatever string that you pass it. In this case, our function doesn't return anything, and then the body of the function is encapsulated in these curly braces. And this function in this case is declared above our main function because our main function uses it. So it needs to be declared somewhere above. Here we have our example main function. We could pass just directly a string in quotes, say Sally, in which case if we run this, it will print to the command line, hello Sally. We could also explicitly declare and initialize a variable. Let's call it name and assign a value of John to it. So then if I passed that variable to our function, then it would do the same thing, except for it would say hello John in this case. And we should also note that we have to include the context.h header file, and it has to be above where we defined say hello. The reason for that is because we're using the cout and endl from the IOStream library. And so we need to define everything for those calls beforehand. And so those are defined in the header file included in context.h. So then the compiler knows about those when it goes to define this function say hello, which also needs to be defined before our main function because it needs to know about that before it actually compiles our main function. Just to illustrate the point of passing the incorrect type to our function, if we were to declare and initialize some variable called a and assign a value of 5 to it that is an integer, and we tried passing that to our say hello function, this would give us a compile time error, and it would say that the argument type is not compatible because it's expecting a string. We gave it an integer, and so it doesn't know what to do with that, and it will flag it as a compile time error. We could also define our say hello function in a header file. So if we had some header file called hello.h, we could put this code into that header file, and then we could simply include it in our main.cpp file. Again, the order here matters. It needs to be included after context.h because the function inside hello.h needs headers from the context.h file, and then all of that needs to be before our main function. But this allows us to have a more compact file. Our code is much more compact because we've put all of those definitions in our header file. Next, we'll talk about vectors. Vectors essentially store multiple values together in one data structure that you can index later. If you're not familiar with vectors already in some other programming language, may be called arrays. I would encourage you to go find a video that talks a little bit about how vectors or arrays and indexing works. But assuming that you're relatively familiar with vectors or arrays in a different language, there are some differences in C++ that may not be the same as what you're familiar with. A big one is that the vector index starts at 0, not 1. So if you're translating code from MATLAB, for example, this is going to be a big source of errors. So you have to remember that the index always starts at 0. Another thing is that you need to explicitly allocate space in your vector if it gets bigger. So it won't automatically just expand the size of your vector based on your index like it would in, say, MATLAB. So you have to explicitly tell it you want to allocate space. Finally, vectors themselves are only one-dimensional. You can have multidimensional vectors, but these are essentially just vectors of vectors. And they're not a matrix as you might think of it, because each index can have a different length. The vector within the vector can have different lengths, so it's not a square matrix as you might normally think of it. Here's an example code where we're dealing with vectors. So the vector is in the standard library, so we need to use the correct namespace. We declare the type of our vector in angle brackets, and it can use any type. It's essentially a template, so it can use any type. And then we give it a name. Here I've named it myvec1. And then I'll go over several different ways that we can initialize the values within our vector. If we want to just do it cleanly in a single line of code, this is how you would do it. You would use these curly braces, and then each argument separated by columns in those curly braces would specify a value. Here, it's going to automatically declare it. It's going to expand the size of our vector to have 3 elements, and then it's going to assign the first, second, and third value as we specified here. So it's doing a lot of things in one single line of code. And as I've said several times before, you don't need to include the vector header file. It's already included in the context.h header file. And then this example is just indexing a value in that vector and then printing it to the command line. Here it's indexing at 1. And so this should output to the command line a value of 2 because it's the second value in the vector. Keep in mind that, again, we're zero indexing our vectors. Here's a second example of how we could initialize a vector. Here I'm calling it myvec2. And after this first declaration, it is now uninitialized, so it has length of 0. Here I'm using the pushback member in order to increase its length by 1 and then assign the value at that last position. So as we run this first line, our length is 0. When I call pushback, it's going to make its length equal to 1, and then it's going to assign at the last position a value of 5. And then when I call that again, but with an argument of 2, it's going to increase its size again, and then add in or assign a value of 2 at the last position, and then so on and so forth, however many times that we want to call this. So after running the second bit of code, myvec1 and myvec2 should be exactly equal to each other. They'll have length 3 and have values of 5, 2, and 3. Another way of doing this would be to declare and resize the vector in one single line of code and then assign values at each of the different indices. So this first line here is declaring a vector called myvec3. And as we've used regular parentheses, this is going to resize it to be of length 3. And then we can index each of the values starting at 0, 1, and 2 using this .at member, and then assign value of 5, 2, and 3. So in the same way, this is going to produce the exact same result. So after running all this code, myvec1, myvec2, and myvec3 should all have the same values. And there are 2 different ways to index our vectors. One is using regular, what we would call C-style array indexing, and the second is using this .at member operator. And the main difference between the two is that when we use our square brackets, it's not going to do any checks for the validity of that index. So it's just going to do whatever we say, and it's going to index and or assign at that value. Whereas when we use our .at operator, it's going to do some checks, and it's going to make sure that that index is valid, and it's going to help us with an error message if what we're doing is invalid. So in this case, these would produce the exact same result. They should print out a value of 2 to the command line. However, if we were to index these at an index of 4, let's say, this is out of bounds. So this is not valid. Our vector is only of length 3. So we could index it at a maximum at an index value of 2. If we were to run this code, we would get different outcomes based on whether we're indexing with square brackets or whether we're indexing using this .at operator. If we do it using our square brackets, this may or may not produce a segmentation fault at runtime. It's basically running over the end of the array, and it's possible if it runs to the end of the memory block, it could result in a segmentation fault, or it could just print out garbage values. It just kind of depends, and you can get random behavior as a result. So the safer way of doing it is using this .at operator. It's going to do a check. If it is out of bounds, then it's going to throw a runtime exception that's going to tell you that it's an index out of bounds. And if you're running it in debug mode or using a debugger, then it'll tell you exactly the line number where this is happening. It'll output some error message, so it'll be much easier to debug. The downside to this is that there's just a slightly higher computational overhead for doing these checks, so the one on the left is going to be slightly faster. But for pretty much anything that you would be doing as a user within Helios, I would recommend using the .at operator for indexing, unless you're really sure that your code is correct and it will never be indexing out of bounds. But there's really not a good reason to use the square brackets in most cases. I mentioned before multidimensional vectors or a vector of vectors. Here's an example of doing that. Here we have a 2D vector. We're going to declare it by nesting 2 vectors on top of each other. So basically what this is doing is first creating a vector of floats, and then we're creating a vector of a vector of floats. So within the curly braces, this gives the type. It can be any type that we want. So it's just the type is a vector of floats. This effectively gives us a vector of vectors, or a 2D vector. I've called it vec2d, and because I'm using parentheses with a value of 3 as the argument, this is going to resize it to be of length 3. This is going to create our outer vector to be of size 3. This is going to create 3 vectors of floats in each of the 3 positions of this vector. If we index our vec2d at some value, this is indexing our inside vector of floats. So each of those 3 indices are a vector of floats. We could assign them using curly braces or using pushback. They don't have to be the same size. This is a nice feature. It doesn't have to be a square matrix. The downside is that it can be a little cumbersome to use, and you don't have things like matrix slicing that you would in other languages. If we wanted to index that 2D vector to get just a single float value back, we would just index it or call that at operator twice. So if we were to index it at 1, that would be indexing our different vectors of floats. And then if we index it again, that's going to index our actual float value within that particular vector. This should result in B having a value of 2. All right, moving along to for loops. There are also some aspects of for loops in C++ that are probably different from other languages you've worked with. I'm assuming here that you have some general idea of how for loops work, and we're just talking about the differences in syntax between C++ and other languages that you might be familiar with. So a main difference is that you need to declare the loop variable and its type, which is different than many other languages, especially interpreted languages where you don't have to worry about the type. And then we can also use this ++ or - operator to increment or decrement our value by 1. So this is just a shorthand that you'll see quite often. Here's an example of the syntax for a for loop in C++. We have for, and then in parentheses, we have the conditions that are going to be used for our loop. First, we're going to declare and initialize our loop variable. Here it's just I. It's going to have type of int, and we're going to initialize it to a value of 0. Then we type a semicolon to move to the next part. The next part is the condition that the loop is going to use to continue while the condition is true. Here we want to continue while I is less than 5. So as soon as I becomes equal to 5, it's going to terminate our loop. Then we type another semicolon, and then we have our operation that's executed on each loop iteration. Here, this is just going to increase I by 1 on every loop iteration. So we're going to start out by assigning I equal to 0, and then it's going to run through the loop. It's going to execute whatever is inside these curly braces, and then it's going to increase I by 1, so then I will be equal to 1. It'll do it again, and then so on and so forth, while I is less than 5. Here's a quick example of just printing out our loop variable. This is very similar to what we just saw on the previous slide. Here we've just added some stuff to do inside of the scope of the for loop. Here we're just printing out the value of I. If we were to try to print out the value of I after our loop, so outside of the scope of our loop, then this would produce a compile time error because I has only been declared inside the scope of our for loop, and it will go out of scope once we're done with our for loop. If we wanted to still retain the value, we could declare it outside of our for loop beforehand, and then we could use it within our for loop, but instead we're not redeclaring it again, we're just initializing its value. And then it would run through our for loop, and then whatever the value of I is when it's finished running our for loop, then it would still retain that value. It would still be declared and within scope as we move through our program. So in this case, this should work because I is still in scope and we could print out its value. We also have for loops that are called range-based for loops. It's basically a shorthand for looping over vectors. So let's say that we had some vector that's going to be a vector of strings, and we're going to call it names, and we're going to initialize it with 3 different names. Then we could use a range-based for loop in order to loop over every value inside of this vector. And the way that we do this is we first declare the type and the name of our loop variable, and then we have a single colon, and then the name of the vector that we want to loop over. The type of the loop variable needs to match the type inside of the vector. Here, we're going to be looping over a vector which consists of a vector of strings. And so the type in our for loop needs to be string. And then we've made up some name that we want to give to it. It's just name. And then we could write out directly name here. Notice that we're not doing name at something. We're not indexing it. It's just directly assigned the particular name for that loop iteration to our loop variable, and then we can use it directly. So it's a little bit of a shorthand for doing this. You don't have to worry about looping over some index and then indexing our array. Finally, we'll talk about classes and structures. I'm going to assume that you're more or less familiar with object-oriented programming from some other language. If you're not, then I would suggest looking up a quick video to familiarize yourself with how object-oriented programming works. The basic idea is that you have multiple data values that are all sort of encapsulated into a data object. And the idea is to declare usually multiple instances of this object, which always contains this same member data. So a classical example would be making an address book. In an address book, each group or object in our address book is going to contain potentially the same amount of information, or it may be allowed to contain the same amount of information. Perhaps the person's name, their email, their student ID, could be their phone number, or any number of other data values. Anytime we want to add a contact to our address book, it's going to potentially contain these data values. We don't have to set the values of each member in our object, but they are there in case we want to assign them. In C++, we have something called a struct as well as a class. These are almost the same thing, as we'll illustrate. The only difference is that the members of a struct are public by default, whereas the members of a class are private by default. But if we just explicitly declare which are private and which are public, then there's no difference between these two. We access members of an object, whether it be a struct or a class, using the dot operator. This is similar in most object-oriented languages. And when we declare a structure or a class, we use curly braces to denote what's inside of them, and then we have to put a semicolon at the end, which is an easy thing to forget to do. Here's an example implementation of our address book. We've created a struct here called contact, and it has 3 data members. The first 2 are strings. We have the person's name and their email, and then we have an integer that gives their student ID. We've declared this struct and which data members it can potentially have. Here we have not initialized them, so they're just empty strings and an empty integer value for their student ID. If we wanted to use that contact, then we could declare an instance of that contact. Here I've declared starting with the type, which is contact, so you can treat the structure or the class like any other data type. Instead of int or float, it's contact. It's basically a custom type. Then we have to choose a name for it. Our name that we give to it is my contact. This could be anything that we want. Here it's been declared, but it has not been initialized, so its values are not equal to anything. So I could use that dot operator in order to access its members and assign values to it. So I could do my contact.name and assign a string of Susie. I could use .email in order to assign an email address, and then .sid to assign a student ID. And if we look back at our definition for contact, we can see where these come from. It has 3 data members, name, email, and SID. We recall the type. We have to make sure that we assign the correct type to them. First 2 are strings, the last one is integer. Now, all of the values inside my contact have been initialized. As I mentioned before, by default, if we have a struct, all of those member data values are public by default. So if I didn't put anything to specify whether it's public or private, then it's public by default. Basically, what that means is that a public data member can be accessed by some other function or routine that's not within that object. So in our example here, it needs to be public because we're accessing those data members from outside of that data object. So in this case, we've just put that our members are public. This will effectively have no impact. It'll be the exact same as what we had before because it was already public by default. I could also have made this a class. We said the difference between a struct and a class is that in a struct, the data members are public by default, and in the class, they're private by default. But since we've already explicitly declared that all of its members are public, then there's no difference because it's not assuming anything by default. So a class and a struct would be the same in this case. If I was to declare that my members of my struct were private, or if I was to use a class and not say anything about whether they're public or private, then my code below would produce an error because we need them to be public so that I can access them outside of my data object. If I was to run this code here, this would produce a compile time error. It would say that these members were declared as private, and we can't access them in this scope. They can only be accessed by the struct or class itself. Another common thing that you'll run into within Helios is a class or a struct's constructor. You notice in the code that I showed before, it has potential to go awry because the data members are not initialized by default. If I hadn't run the code to set their values, then something could have gone wrong because, if I forgot to initialize one of the values and then tried to use it later, then this could produce incorrect results in my code. It could potentially result in undefined behavior. We typically have a constructor as part of our objects that initialize our class or struct and bring it into a valid state. Here's an example of a constructor for our contact. The constructor is basically a function that shares the same name as our data object. So our object was called contact. And so our constructor is going to have name of contact. And this can have one or more or zero arguments to it. Here we've written a constructor that's going to make sure that we initialize all of its member variables. So it has 3 arguments. The first is a string, the second is a string, and the third is an integer. So we pass these values to our constructor when it is initialized, and then it's going to go in and make sure to assign and initialize a value to each one of these members. The code below is showing an example of declaring our instance of our contact, but now because it has a constructor, we need to give it values in order to initialize it. We could pass the first argument as a string called Susie, the second argument as the email address, and then the third argument as an integer, and then it would initialize all these data values and make sure that everything was properly initialized and we're not going to get undefined behavior. The plugins and different things within Helios are going to be classes, and so they're going to have some constructor that's going to be used to initialize them typically. We could do other things with our data object. We can also make a vector of these, for example. So if you were actually going to do an address book, your address book would consist of typically many different contacts. We could create a vector called a vector of contacts, and then we could call it address book. And then we could use pushback to insert this contact that we just created. Our objects can also have member functions. We could have some member function that prints out what the name of the contact is. Here I've added a function that just does that. And so we just put that within the definition of our object, a struct in this case. We've put it within the public block, so this is going to be publicly accessible, which means that we can call it outside of our contact. So here we're initializing some contact, and then we could call the member function called printName that would print out the name of that contact. In this case, the contact name is Susie, so it would print out name is Susie to the command line or the standard output. So just one final example to bring everything together. This is an example of a very short Helios program that uses many of these different aspects that we've talked about. So here we're including context.h as we normally would within a program. We have our main function. First, we're going to declare an instance of the context. This is covered in another video, but this is basically the main class of Helios. It's the data repository that keeps track of everything and is passed around from plugin to plugin. Its type is context with a capital C, and then we've given it a name. I've just used lowercase context, but you could call it anything that you want. So it's going to initialize an instance of the context class. This one does not have an explicit constructor that takes arguments. It just initializes everything on its own. Then we've declared a vector of unsigned integers. We're going to use this to keep track of all the unique identifiers or UUIDs for the model geometry that we add. Then on the next line here, we have called the member method load PLY within the context. It's a method because it operates on the members of our class. It's basically the same as a function. So it takes an argument of a string, which is the path to a model that it wants to load a PLY model. And then it returns a vector of unsigned integer. So we can assign that to our UUIDs vector. Then we could use a range-based for loop in order to iterate over all of the unsigned integers within this vector. This corresponds to each of the primitives that were added within this PLY model. Then we could call another method of the context called getPrimitiveArea. This takes an argument of an unsigned integer, which corresponds to a UUID. Then we could assign the output of that function to a variable that we called area. This returns a float, so we need to make sure that the types are all consistent, both with the arguments going in as well as what's being returned from our function. And then we could just write its value to the command line. And that's it. You'll see more and more of this as we go through to reinforce some of these concepts, but hopefully that was helpful in just familiarizing yourself with some of the differences between C++ and other languages that you may be familiar with.